So today we will be looking at some of the topics on discrete time systems. We have covered a number of concepts in discrete time sequences. If you look at the study plan for weeks 1 and 2, those topics that have been ticked are topics that we have covered in the last few sessions, and today we will be covering the remaining topics. So let us take a look at the material that we have covered and then move forward today. In terms of reading, we have now reached section 2.3 in the textbook Oppenheim and Schaefer, and in the reference book Rawat, it is in, we are completed chapter 1. So please follow along, and that will be very helpful. So very quickly, the unit sample delta of n is a signal which has got a value equal to 1 at n equal to 0, and it is 0 everywhere else. Delta of n minus 1 is delayed by 1 unit of time. Delta of n plus 2 is advanced by 2 units of time. So using this as the basic framework, we said that x of n, any sequence, can be represented as a superposition or a sum of scaled delta functions. So x of k is the scale value. Delta of n minus k tells you that this sample will occur at value n equal to k. So using this understanding of how these unit sample functions are delayed or advanced, we can get a representation of any discrete time sequence in this form. We also saw that discrete time sequences can be classified as finite length or as infinite length. If they are finite length, we know how to calculate the length of the sequence, n2 minus n1 plus 1, where n1 and n2 are the two limits of the sequence. We can say whether a sequence is a causal sequence or is it a right-sided sequence. Similarly, anti-causal or left-sided, or it does not satisfy either causality or anti-causality. Therefore, we will classify it as a non-causal signal. We highlighted two properties of discrete time sinusoids. The first one is that all discrete time sinusoids are periodic in frequency with a period equal to 2 pi. And that we demonstrated using this particular example illustration. We started from omega equal to 0, pi by 8, pi by 4, we increased in frequency up to pi, and then further increase in frequency started reducing the rate of oscillations. Eventually at omega not equal to 2 pi, we see that its behavior is the same as omega equal to 0. So we see an increase in rate of oscillation up to pi, decrease. So basically this is what we capture by the statement which says that discrete time sinusoids are periodic in frequency with a period equal to 2 pi, and of course any multiple of 2 pi also will satisfy periodicity. Now, discrete time sinusoids are not always guaranteed to be periodic in time, and in order for to check whether a sinusoid is periodic in time, you would have to take 2 pi by omega naught and check if this is a rational of the form rational form n by m, where n and m are integers. M can be any arbitrary integer, and then that gives you n becomes the period, shows you what the period is equal to. So these periodic functions will satisfy the condition x of n plus any multiple of n uppercase n, which is the period. So this uppercase n is what we call as the period. Okay, so in this calculation, n will come out to be equal to the period of the periodic sequence, Okay, so if you substitute x of n plus any multiple of the period, you should get back the original signal. So this is the property, and that is true for all values of n, and that's the definition of period. So can a sinusoid be periodic in time and in frequency? It will be periodic in time only if it satisfies this condition. So you always have to be very clear about that. However, if you look at the change with respect to frequency, and you keep increasing the frequency, you will find that there is an inherent periodicity with a multiple of 2 pi. Now, if you remember, when we mentioned that we would like to look at a ramp function, and the ramp function we said has a value n times u of n. So if you were to sketch it at time n equal to 0, it has a value 0. At n equal to 1, it has got a value equal to 1. At 2, 2, 3, 4, and so on. So basically, it keeps increasing. So that is what we call as the ramp function. So how can we verify these three properties? So let's take the first of the three properties. We said the ramp r of n is equal to k equal to 0 through infinity. So, the first term is k equal to 0. So, this if you expand it is 0 times delta of n plus 1 times delta of n minus 1 plus 2 times delta of n minus 2 and so on. So, that is exactly the, if you remember the delayed unit sample functions and that are scaled. So, delta of n minus 1 is a unit sample function that occurs at n equal to 1, it has got a height of 1. Delta of n minus 2 occurs at n equal to 2 and has got a height of 2 and so on. So, this you can verify just by sketching that this gives you the equivalent of the ramp function. Now, the next representation says we are going to look at u of the summation goes from, so basically let us sketch u of n. U of n is a sequence that starts at n equal to 0 and has got value equal to 1 for all positive. So, this is n equal to 0, 1, 2 and before that it is negative, it is 0. Okay, so, let us just move this a little bit to the right. Okay. Now, R of n by this expression is a summation from minus infinity to n minus 1 of u of k. U of k is basically the unit step function. You can wherever k has got value equal to 0, you will have a sample value equal to 1 and then everywhere else you will basically have a so, sorry, wherever the argument is equal to 0 or greater than 0, you will get a value equal to 1. So, R of 0 basically starts at minus infinity. So, let us stretch this a little bit further down. It starts at minus infinity and keeps summing all the values up until n minus 1. So, R of 0 is a summation all the way up to n equal to 0 is minus 1. So, this is the summation for R of 0. Notice that it has been summing over all 0 valued samples. Then R of 1 will go all the way to n equal to 0. So, you will get this is R of 1. Notice there is one non-zero value, so that therefore, that will give you a sample 1 for R of 1. So, R of 1 according to this expression R of 0, all 0 valued samples were added, here one non-zero valued sample was added, then R of 2. R of 2 from minus infinity it goes all the way up to 1, there are 2 non-zero values, so therefore, R of 2 equal to 2 and so on, you can see that you will start to get the ramp function. So, that is the second of the through. So, the idea is so you should be able to look at the expression and verify, sketch it, look at what the calculation is being done and therefore, you are comfortable with that. The third one is very interesting. It says it is a summation, let us write this down, okay, R of n we can say is summation m equal to 1 through infinity. So, it is if you write it down it is u of n minus 1 plus u of n minus 2 plus u of n minus 3 and so on all the way up to u of n minus infinity. So, what is this very interesting. So, what is u of n? U of n starts at time n equal to 0. Okay, so, this is u of n, this is u of n. Okay, but what we need is u of n minus 1. U of n minus 1. So, this is the origin that has got, it's got zeros all the way from minus infinity to here and at this point it starts to become, this is u of n minus 1, the unit step delayed by 1 unit of time. Okay. Now, what is u of n minus 2? U of n minus 2 has exactly the same thing, maybe easier for me to copy from here, edit, copy, paste, okay, u of n minus 2, okay, u of n minus 2, the second sample is also equal to 0, everything else is here, okay. Same thing if I were to do it one more time. Okay, I have have to move it a little bit to the side so that I don't overlap other figures. Okay, u of n minus 2. U of n minus 2 basically will have another 0 valued sample. This was also 0 valued sample. Okay, u of n minus, no, did I make a mistake? U of n minus 1, n minus 2, of n minus 3. Okay, so this will have one more 0 valued sample. 1, 2, 3 starts. So this one starts at 3, 0, 1, 2, 3, and this is 4 dot 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 dot. This is n. This is n. Okay. All right. Let's take a quick look. If we add these signals together, that is the first signal plus the second signal plus the third signal and go on. So you can see for n equal to 0, all are 0 valued samples. Anything to the left of it is all 0. Then at n equal to 1, the first signal is has got a 1, everything else is 0. The second, when you move to 2 of them are non-zero. Then you move to 3 of them are non-zero. So if you add them together, you will start to see the appearance of a ramp. So you can verify that this is also another way of getting the ramp function. So let me just indicate that this particular diagram belongs to part 3. Okay, part 3. So this is the sketch for that, and that's what we have. Okay. Then we looked at sequences. We defined the property of an even sequence, odd sequence, and if they are complex valued, to talk about conjugate symmetric, conjugate antisymmetric, and of course the basic definition of a periodic signal is that value of uppercase n which satisfies x of n equal to x of n plus n for all values of n. We want to choose the smallest integer that satisfies equation 1, and that is the condition for periodicity. Okay, we looked at the step of downsampling. That means throwing away some samples. So downsampling, we saw an example of a downsampling by a factor of 2. We threw away every alternate sample. If you are basically going to retain only those samples which correspond to multiples of m. If m is equal to 2, you retain 0, sample number 2, sample number 4, and so on, and so that is what we see as the downsampled sequence. Now we can also think of the counterpart, which is the upsampling. So where you are introducing zeros between samples. So upsampling by a factor of n, that is the most general form, means that you retain the sample whenever it is a multiple of n. In between we insert zeros. So for example, if you have x of n 1, 2, 3, 4, 5, 4, 3, 2, 1, 0, upsampling by a factor of 2, it will become 1, 0, 2, 0, 3, 0, and so on. Upsampling by a factor of 3 will be 1, 0, 0, 2, 0, 0, 3, and so on. So that's what we are seeing here as upsampling and downsampling. The interesting part comes when we have to do both upsampling and downsampling as part of the operation, and we gave a guideline that always we prefer to do upsampling first, followed by downsampling. That's usually a general procedure to follow. So the homework that you were asked to look at basically said, how would you obtain the sequence x of minus m by nn minus n naught. Okay, so let's just highlight that just as a way of verifying. So the first step would be to define an intermediate sequence. The first step is shift. So x1 of n is equal to x of n minus n naught. The second one is upsampling. Okay, the second upsampling, which one is upsampling? N divided by uppercase n. So we are going to define a second sequence x2 of n, which is x1 of n by n. Okay, and notice that you will also have to specify that this non-zero values will occur if n equal to 0, plus minus n, plus minus 2n and so on, and it will be equal to 0 otherwise. So, this is the upsampled single. You have inserted some number of n minus 1 zeros between successive samples. Okay. Third step is downsampling. So, x3 of n is equal to x2 of mn. What did you do? x2 of n is equal to x1 of n divided by n. So, this will be equal to x1 of mn divided by n, okay. And what are the conditions? If n equal to 0 plus minus n plus minus 2n and so on equal to 0 otherwise. Okay. So, basically the original condition still holds. So, otherwise. Okay. So, that is the definition of x2 of n. It is defined to be equal to this, the argument divided by n for these values. So, same condition holds. Okay. Now comes the last and final step. So, we say that the final step y of n is equal to x3 of minus n. Wherever there is n, you replace it with minus n. So, that will come out to be x2 of minus mn, that will be equal to x1 of minus mn by n. Again, the condition will be if n equal to 0 plus minus n and so on, 0 otherwise. Okay. And what is x1 of n? x1 of n is this argument delayed by n naught. So, x of n, this is equal to x of minus mn by n minus n naught if n equal to 0, sorry, n equal to 0 plus minus n and so on, and 0 otherwise. Okay. So, do it step by step, follow the systematic way. Always start with a shift first, that is your first intermediate function. Second intermediate function, if you have to do any time scaling, and if you have to do both upsampling and downsampling, do the upsampling first, followed by downsampling, and then as a last step you can do the time reversal. I hope you will have an opportunity to look at it more carefully, look at some of the examples that are given in the assignment, and this will be very helpful to you to practice this particular aspect. All right. So, now we are at a point where we would like to try some practice problems. So, I would like you to write down these practice problems and then try it out and really master these concepts.